Okay, so we are live again, and welcome everybody to the next seminar of the International Institute of Physics. And as usual, it's a great pleasure to have with us Reinhold Egger from the University of Düsseldorf. So Reinhold really doesn't need introduction. He's a very frequent visitor. And today he will tell us about detection of non-Abelian anyons with Majoranas. Thank you.
Yeah, good morning, everybody. It's always a great pleasure to be back to Natal. And the story today is about how we could possibly see non-Abelian statistics for the simplest type of non-Abelian anyons in a real experiment. And our proposal is that this is possible by just measuring a conductance in a suitable device. And the work is based on this preprint here with my postdoc Andrea Nava, Fabian Hassler from Aachen University, and Domenico Giuliano from Cosenza University in Italy. And you can find all the details in this paper. So the plan for this lecture is that I start with a gentle introduction to topological quantum computation and non-Abelian statistics. And the workhorse I will use are chiral Majorana fermions. So these are sort of edge states like in a fraction quantum Hall, but Majorana fermions. By themselves, they are just fermions. So they are not Ising anyons, but you can generate Ising anyons as domain walls or so-called edge vortices in chiral Majorana fermions. And since these are moving modes, like edge modes of a fraction quantum Hall system, these are also flying Majorana zero modes. So they're not static like the usual Majorana zero modes that people consider, but they move in space, and we will see that this gives them a resilience against disorder. And then I will show that by using a Majorana interferometer, you can use the AC conductance, finite frequency conductance, to reveal the so-called topological spin of these edge vortices, which basically means you can probe non-Abelian braiding in conductance. So that's the plan. And let me start with anyon braiding. So consider particles that have neither fermion nor bosonic statistics. So under an exchange, they just have either a scalar phase factor different from plus or minus 1. These are the so-called abelian anyons, or the non-abelian anyons, which are more complicated, where the initial state and the final state are connected through a unitary matrix. Yep. And you can view this in a space-time diagram. Here, space-time. So here you have two anyons, and now you move them around by basically an adiabatic interlacing of world lines in space-time. This is called braiding, and this braiding process is important because for non-Abelian anyons, topologically distinct braids, meaning there is no continuous deformation which breaks or cuts world lines, will be represented by different unitary matrices. Yeah? And so you end up in different final states depending how you do this braid. And because no continuous deformation can sort of mess up things, you are protected against disorder or noise effects. So this is called topological protection, and that's why such unitaries can be used as building blocks for a topological quantum computer. Such braiding operations cannot connect locally indistinguishable ground states. So when you have such a braiding, the two states that are connected by this unitary, you can never distinguish these ground states by local operations. You would need to do global measurements. So they're only different on a global scale. And that makes them useful for fault-tolerant quantum computation, because normally errors in typical devices, they act locally. So there are local error sources that generate the problems that you have to fight with. And since these local sources cannot really distinguish the states, they don't mess up the quantum information. And that's why these ideas of using non-abelian anyons and their braiding properties as the basic elements of topological quantum computers is so attractive. So the simplest type of non-abelian anyon is the Ising anyon, which is basically a vortex carrying a Majorana zero mode at zero energy. So let me briefly introduce the concept of Majorana fermions. And you can consider a set of Majorana fermions as described by operators gamma I or gamma j. So they can sit at different points in space. And they're described by self-adjoint operators. So gamma is equal gamma dagger, meaning the particle is equal to its antiparticle. But there are fermions. Yeah, particle equal antiparticle is a common feature for bosons. For fermions, it's much less trivial. So different Majoranas here really just anti-commute like fermions. So they obey this Clifford algebra, but gamma squares to 1, unlike the fermion which squares to 0. So in that sense, the annihilation of a particle and an antiparticle recovers the previous state. Yeah? And it also means that gamma dagger gamma is just gamma square. So if we want to define a counting operator of whether a Majorana fermion mode is occupied or not, we see that this doesn't work. The occupation number of a single Majorana fermion is ill-defined. It's just a number. Yeah? It doesn't tell us anything. What you can define is a counting operator occupation number for pairs of Majoranas. So you can only count whether pairs of Majoranas are occupied or not. And to see that, you introduce a conventional complex fermion C with the usual algebra of fermions, and basically the real part and the imaginary part are represented by the different Majorana fermions. This is only non-trivial if gamma 1 and gamma 2 are spatially separated. You can always do it, but it will not help you in any sense. So the important point is that the gammas are at different locations in space. And in that case, you have a single qubit, basically a two-state system, because C dagger C measures whether the fermion is occupied or not. It's 0 or 1. And in that sense, these gamma 1 and gamma 2 are equal weight electron-hole superpositions. Yeah, so that's just a Majorana fermion primer. And here you see again this picture of having two Majoranas at spatially separated points. Together they form a zero energy fermion mode. And since you have two states that are degenerate, you can use that in principle as a qubit where the information is stored non-locally. Information is distributed here non-locally, and because of that, it's topologically protected. Local error sources cannot mess up the quantum information. Okay, now Ising anyons, as I said, are the simplest type of non-abelian particles. And you can think of them, for instance, as a vortex core in a topological superconductor, like a p-wave, two-dimensional p-wave superconductor. And then you look at the vortex, and that's shown here. So the energy versus the space here would be a vortex. And if the pairing potential shows something like this, so it goes to 0 at a certain point, if it's a topological superconductor, it must have a zero mode, this Majorana zero mode at 0 energy. However, in a real topological superconductor, because it has a finite vortex core, there are also normal subgap states. And these are called Caroli-Matricon-Dechaine states. And these states are shown here. These are bound states in the vortex. They live typically at finite energy, depending on the size of the vortex core. And in fact, these bound states give a lot of trouble because they can easily mess up the physics attached to Majorana zero mode or give confusing signals. Anyway, if we ignore that and just take these Majorana zero modes, the idea then is to move around these vortices in space and do the braiding. This is sort of illustrated here, and mathematically, these gamma operators carry branch cuts with them in space-time. So they cause a branch cut, and every time a world line of this anyon crosses such a branch cut, you get a minus sign. Yeah? And this can be used to generate the unitaries. Yeah, for instance, in this picture here, time runs in this direction, and you braid gamma 2 and gamma 3. Gamma 1 and gamma 4 are not touched. And in that case, you will generate a certain unitary gate acting on your states. Now, I can't emphasize enough, for useful implementations, we need a robust and reproducible hardware platform. That's one of the biggest challenges at the moment. And if we step back first and look at the Abelian case, that was a big breakthrough about 4 years ago. The groups of Gwendal Fèvre in France and Mike Manfred Purdue in the US, they managed simultaneously to show Abelian fractional statistics. So they showed when you exchange two Abelian anyons, then there is this complex phase. Yeah? Normally for bosons fermions, it's just plus or minus 1. For Abelian anyons, it's e to the I5 with some fractional angle. And these were the first experiments that have shown the expected statistical exchange angles of anyons in the fractional quantum Hall effect at the nu equal 1/3 state. That's the simplest state, and the exchange angle is 2 pi third. And they saw this by doing shot noise and anyon collision experiments. So a typical sample is shown here. You basically generate with quantum point contacts. Here are the edges carrying these fractionally charged anyons. And then you let them collide or probe shot noise. And in this signal, one can sort of see how they braid. So you can see how the statistical exchange angle shows up. These are difficult experiments. It took them more than 20 years to bring the samples to a perfection that allowed them to do such experiments. So it was really a major effort. It was predicted in the 1980s that this should happen, and only now it has been seen. Recently, it has been pointed out there could be simpler schemes to see this Abelian fractional exchange phases, namely by just measuring conductances. And of course, that would help once you go to more complicated non-Abelian cases. Conductance could be sort of you define a conductance between two terminals, whatever terminal is suitable to extract information about this phase. So it's not just the Hall conductance, but a more complicated device that they consider here. And of course, you need to have processes where effectively particles braid around each other. But then in the end, the signal is still contained in a conductance. Yeah. So the question is then, how can we hope to observe non-Abelian braiding? So far, the only experimental evidence is from quantum simulation on transmon qubits, so circuits, these Google circuits with hundreds of transmon qubits. They allow to do quantum simulations, and basically you can, with clever engineered circuits, mimic Majorana braiding, and this has been done in these two papers. And so this is evidence for Majorana braiding. But of course, this is not useful if you really want to do topological quantum computation. Then you would rather do a surface code or color code directly on your transmon circuit. You wouldn't go the detour to first do Majorana fermions artificially and then braid them. But this is sort of a demonstration device. Now, of course, you are all aware since 10 or 12 years, there was a massive effort to make Majorana zero modes and bring them to life, generate qubits, especially in Delft and Copenhagen, but also in other labs. The problem with these platforms is that disorder, so in these cases, the Majorana zero modes were localized modes. For instance, in 1D nanowires, the ends should carry such Majorana zero modes. The problem with these platforms, also with the topological superconductors, where the vortex carries the Majorana zero mode, is that disorder causes conventional subgap Andreev states, and these subgap Andreev states compete with the Majorana zero mode. Yeah, and so they can mess up the signal, that they're hard to distinguish. There is a heroic effort in the Microsoft Station Q group, where 150 people developed a topological gap protocol designed to distinguish the effects of Andreev states and Majorana zero modes. And with a certain confidence level, then they can tell, yeah, here there sits a Majorana, here it's an Andreev. As far as I know, they haven't been able to do a qubit, let alone braiding yet. Yeah? But maybe one will see it eventually. But I mean, the main enemy here really is disorder. Now, our idea here is that we use the analogy to the fractional quantum Hall case, also exploited in the Abelian case for demonstrating fractional statistics. Because the chiral edge modes, they are naturally protected against disorder. Yeah, it's a unidirectional mode. If there is some disorder centered, it can just move around it, but it will not be backscattered. Yeah? Because it's chiral, it cannot be disrupted by disorder. So what we will do is we will here test braiding using the edge vortex excitations of chiral Majorana fermion modes, which are flying Ising anyons or Ising anyons. And here the chirality of these Majorana edge modes directly gives you an intrinsic protection against disorder. Yeah, that's one of the key ideas. The question then is which quantity to probe. Similar ideas have been around for fractional quantum Hall cases, states with non-abelian particles. The most famous one is the 5-half state, which should have an Ising anyon. And the existing proposals propose to study shot noise. So this old proposal by Bonderson and co-workers, and more recently Lee and Sim showed how one could do that to see braiding from shot noise. Now there is a certain difference from the devices I will consider, which in our case allows us then to make a simpler proposal. And our proposal is basically relying on chiral Majorana interferometers, and they go back to proposal by Fu Kane and Nielsen, Akmarov Nielsen and Benacker. So let's consider a system where we have a topological insulator, three-dimensional topological insulator like bismuth selenide. It has a bulk gap, but these topological insulators on the surface, they have Dirac fermions, a single cone of massless Dirac fermions. And these Dirac fermions have been seen in many, many experiments by ARPES, by transport, so there's no doubt they are there. And you can gap them out by deposition of either a magnet or a superconductor. And so the idea of these gentlemen was, let's put, for instance, in this central region, a superconductor. It might harbor some vortex or not. So here the deposition on the topological insulator, there's a superconducting layer, just a plain S-wave BCS superconductor. underneath, it will induce a topological superconductor phase in the two-dimensional layer. So in the two-dimensional layer, underneath this superconductor, we have a topological superconductor with some induced pairing gap. Then in the outside region here, the idea is to deposit a ferromagnet, and let's say with spin down. In that case, there's a different type of gap. So both these phases, this is basically a quantum anomalous Hall insulator, while here we have a topological insulator. Both states are gapped, so there are no low energy states, but at the interface in between, there is a gapless mode. And this gapless mode is exactly a chiral Majorana mode, basically half a fermion mode. It's chiral in the sense that unlike the Majorana zero modes, which are fixed in space, this mode moves around in this way with an edge velocity. Yeah, so it's basically a half a fermion, namely a Majorana fermion, and this such an edge mode can be created by having interfaces between magnetically and superconductively gapped regions on the surface of a topological insulator. Yeah. And this gapless one-dimensional chiral Majorana mode, so chiral always means unidirectional, it can only move in one direction, is charge neutral. Doesn't carry charge. The charge is here always taken care of by the condensate of the superconductor. Now the next step that these gentlemen looked at was to create an interferometer by having here a magnet with magnetization down and here up. And so then here, between the different magnetizations, you have a chiral Dirac mode, which you can use as an incoming channel for electrons. So you can attach this now to some normal metallic lead at some bias voltage and send in electrons. Now, along this direction, the direction of the Majorana fermion is like that. But since we have opposite magnetization here, it must go like that. So at low energy scales, because there is a gap both in the magnetic region and in the superconducting region, the only modes you have are these chiral Majorana modes. So there's no other way than that this Dirac fermion channel will split into the two chiral Majorana fermions. And that should work with unit efficiency if you are at low enough temperatures. And so the incoming Dirac channel is injected, goes around, and then with unit efficiency, it goes out again. And now depending on whether there is a vortex or an even or an odd number of vortices inside here, the electrical conductance that you measure in this interferometer was predicted to be E squared over H times plus or minus 1, depending on whether the number NV of vortices is even or odd. So if it's odd, then basically you send out holes. If it's even, you send out electrons. That's connected to these branch cuts because this central Majorana zero mode basically has a branch cut sitting around, and then the Majorana fermions will also change the sign effectively. Yeah, so this is this proposal, quite famous, and the essential feature is that we here have co-propagating Majorana modes. They move in the same direction. And that's very difficult to have in a fractional quantum Hall case. So that's the big difference, which allows us to use simpler schemes for electrical detection of braiding. So how can one describe these chiral Majorana edge modes? So they arise. So always underneath there is the topological insulator. And now we look from top and we deposit either superconductor or this magnet, giving rise to the quantum anomalous Hall insulator. And then we have at the interface this chiral Majorana edge modes. You also would get it just between a superconductor and a plane insulator. In any case, the edge Hamiltonian looks like this. So there's an edge velocity v, and the Majorana fermions are described by abelian fermionic particles with a field gamma of x, which is equal to gamma dagger of x, and they obey this anti-commutation relation. So they are just plain fermionic particles, but in a sense, only half of the fermion, because they have to be real. Yeah? Gamma must be equal gamma dagger, so they cannot carry phase factors like usual fermions can. So how to get Ising anyons, non-abelian Ising anyons? The way is to introduce domain walls. So these are called chiral edge vortices. They usually have the operator symbol sigma. If we have one at position xv, their job is to insert a minus sign on that side and leave it like that. So for x less than xv, applying this chiral edge vortex will give a minus sign here. So in a sense, it's a domain wall that gives you plus or minus signs. There's no other possibility because gamma is a real field. You cannot have a general phase on both sides. So these sigmas are domain walls for the phase, and they are robust because the Majoranas are real valued. You cannot have a phase that could then vary by a little bit. So they're really robust, and they're disorder resilient because of the chirality. They flow along with the edge. And each of these edge vortices now, you can think of them like a vortex on this 1D edge, and each of them binds a Majorana zero mode. So that's the Ising anyon. So this vortex together with this bound Majorana zero mode at zero energy. If you know the Chakif-Rebbe calculation or the Chakif-Rebbe mode in a one-dimensional chiral Dirac channel, if you have a mass kink, it binds a zero energy fermion. And now we here just have half of this. So because of the Majorana nature, we bind not a real fermion, but not a complex fermion, but this Majorana zero mode. And this vortex has no core. So you have no problems with these Caroli-Matricon Deschênes states. It's basically just a coreless vortex. So it only has this Majorana zero mode, nothing else. And that's the Ising anyon that we are after. Yeah? So these edge vortices. No, even physically, they should have no core because of this property that the Majoranas are real valued. Yeah? So it just inserts the sign -1, +1. And so that basically doesn't allow you to have other bound states at this vortex core. That's the big advantage of this proposal. And as I said, the big difference to the fraction quantum Hall, so I think the pointer, yeah, here it is. The fraction quantum Hall interferometer is that the Majorana fermion modes and also the edge vortices, which are co-moving with the Majorana edge mode, are now co-propagating. And so you get simpler schemes for accessing the braiding statistics. I should say that in the Benacker group, since 5 years, efforts have been made to inject deterministic or classical edge vortices, basically by using a finite magnetic flux pulse. You can imprint the -1 to +1 domain wall at a given time and space, and then you do basically a guided braiding around bulk vortices by doing time domain charge measurements. Here, in contrast, we are after quantum edge vortices, because these edge vortices have been studied in CFT, conformal field theory, and they have very interesting properties that basically are really Ising anyons. These deterministic classical edge vortices are not Ising anyons. Yeah. So again, there are no problems with in-gap states. We have no normal core. They're insensitive to disorder, the naturally movable non-abelian particles. You can braid them around static counterparts. So if there is a bulk vortex inside the sample, or you can braid them around themselves. And the braiding here is really hidden in the equal time correlation function of this sigma operator. And this has been worked out by who else? Alexei Kitaev in 2006. He has it in this paper. So I think this died. So the correlator has now a decay with space where you have a conformal dimension h sigma, which is 1/16. And remarkably, it has this prefactor e to the 2 pi I s. S sigma is also 1/16. This is called the topological spin. And if you exchange them, basically you have to sort of take care of this complex phase factor. In that case, it's just e to the I pi over 8. Yeah, and we will see that this topological spin is related to the non-abelian braiding of an Ising anyon. So here is our device. It's basically just the previous Fu-Akmarov interferometer. So you have leads on the left and right side. Then there is superconducting. One can hardly see it. Yeah? So there is a superconducting region here. On the top, the blue region is a magnetically deposited layer in up direction. Then we have one in the down direction. So again, you have incoming chiral Dirac and outgoing chiral Dirac states. And at these points here and here, they are split up and move around like in the previous interferometer. The novelty now is to add a central island. So one can not see this very well. So here should be a line junction. And here should be a Josephson junction, a line junction that sort of defines here a central floating superconducting island. So everything is again on top of a topological insulator. So underneath the superconductor, you have a topological superconductor. Underneath the magnets, you have quantum anomalous Hall insulators. And so these lines are chiral Maiorana fermions co-propagating. And the central floating island is basically defined by a charging energy, EC, related to the capacitance, while here we have outer regions that are still floating and basically allow you to still have this unit efficiency process of converting the incoming and outgoing Dirac fermions into the Majorana fermions. Yeah. Okay. Oh yeah, that's better. And here, for instance, these could be bulk vortices where you bind Majorana zero modes that are sort of spatially localized. Okay, so at x equal plus L, we have one line junction. At minus L, we have another one. And such Josephson junctions are characterized by a Josephson energy EJ, basically how easy can Cooper pairs tunnel across the Josephson junction. And we want to operate this central island in a regime where EC is small against EJ. That's the same regime as people use in transmon devices. In that case, we can have phase slips where the dynamical superconducting phase on that island, which is now not fixed to zero anymore because, so here it's zero because we have grounded superconductors. In the center, it's a floating piece, and that means the phase is dynamical. It's a quantum variable. It can change and it can spontaneously flip by 2 pi. Plus or minus 2 pi. This is called a phase slip. And in this regime here, such phase slips are fast, so they happen on a short time scale, and they occur at a rate that is estimated to be given by a plasma frequency suppressed by this exponential factor. So the plasma frequency is here the largest frequency in the problem, given by this expression. And so these rates are typically small. Yeah? But you can tune them by changing the parameters of your device, by changing the charging energy or changing the Josephson energy. In any case, what happens now if you have a phase slip? If you have a phase slip, it means that for the Maiorana edge modes, there will be a sign change between these 2 points, between these 2 points, these 2 points, and these 2 points. So that means a phase slip generates 4 of these quantum edge vortices or annihilates 4 of them simultaneously. Yeah? So the phase slips here really generate or annihilate these quantum edge vortices signaled by the red stars at these positions. Yeah? So let's look a bit at the fine print. So we assume that the plasma frequency here, omega p, is large against this rate for producing the phase slips and also big compared to the induced superconducting pairing gap. In that case, phase slips are just effectively time-local events. Moreover, we assume that the width of this strip is large against the coherence length of the superconductor. In that case, upper and lower Majorana fermions don't have an overlap. Yeah? Otherwise, if they can talk to each other, then it messes up the physics. So they don't hybridize except at the points at these junctions. So at the junctions, we allow for transfer or tunneling of Majorana fermions from top to bottom and back. And the third key assumption is we are at low temperatures below the pairing gap such that there are no above gap quasiparticles, and the transport through the interferometer only proceeds through these chiral Majorana edge modes. Yeah, because there is a bulk gap. So there's no other chance to move electrons from here to here than going through these Majorana edge modes. And once again, we have this protected Dirac-Majorana conversion because we included these grounded pieces of superconductors. So the conversion happens with unit efficiency. So in our analysis, that's a technical point. We assume that there's an equal path length on the upper and the lower branch. I can comment on deviations of this assumption later, but let's assume that for now, this assumption allows us to use the technique of chiral bosonization, which is very convenient here. So the idea is you first combine the two one-dimensional chiral Majorana fermions to one chiral Dirac fermion. Yeah, so psi of x is a right-moving Dirac fermion with gamma 1 or gamma on the top and gamma on the bottom as real and imaginary parts. Then once you have this Dirac fermion, you can bosonize it. It's a one-dimensional chiral Dirac fermion. You can bosonize it using a chiral boson field. So a boson field that also moves only in one direction. And the big benefit of that is that the edge vortex operators have a simple representation in bosonized language only. I wouldn't know how to write them down in the fermionic language, at least not in an easy way. And this has been spelled out in a beautiful work by Fendley, Nayak, and Matthew Fisher in 2007. They showed by comparing bosonization and a full-fledged CFT analysis that an edge vortex pair at a certain position xj on the bottom and on the top edge, so there's a sigma t on the top and sigma b on the bottom edge. This product is representable by e to the I half phi at this position, but you need an auxiliary spin operator. So this is a spin lowering operator, a spin 1/2 operator that ensures the proper Ising fusion rules. If you have two Ising anyons and collide them, they must fuse either to the vacuum or to a fermion. And this is taken care of by this auxiliary spin. Turns out that the SC component is conserved. So you work either in a sector with +1/2 or -1/2, and this number basically is the total fermion parity, which is conserved in this device. So with this formalism, you can now start doing calculations, and what we are after is the linear response conductance at finite frequency. In linear response, you can use Kubo formula, so you can work in equilibrium by computing current-current correlation function, and then doing an analytical continuation to real frequencies. So we work in imaginary time. Tau is between 0 and beta, beta being inverse temperature. And then in linear response, we can dismiss the voltage term. The Euclidean action has 3 pieces. S0 is the free action. So in the absence of the junctions, that's the free action of a chiral boson field phi of x and tau. And that's quadratic and well known. And if you look at the equations of motions generated by this action, you see it's really a right-moving boson field, as it should. Then the next part, SF, describes the Maiorana fermion tunneling, so that Majoranas can tunnel from one edge to the other at the Josephson junctions. And so the J runs over these 2 Josephson junctions, and we have a strength lambda J for each of these tunnel processes. And then it has, in bosonized language, a very simple representation, just linear in dx phi. And so you can take into account this piece just by a unitary transformation in an exact manner. The most challenging or difficult term in this problem is the last one due to edge vortices, and that has a prefactor related to the phase slip creation rate, gamma. And then it is a nonlinear action. It comes with a cosine. There is a field W minus, which is basically the difference of these chiral boson fields at the right and at the left junction. Then there is a shift here that comes from the braiding. So it contains this topological spin, this S sigma equal to 1/16. And finally, there can be a shift due to a backgate charge offset parameter, because you could have a backgate where you can tune the desired number of particles or electrons on the central island. And so this is tunable by some backgate voltage. So that's the problem we have to tackle. And because it's a nonlinear problem, it's not so easy. But what you can do as a first step is to rephrase this as a quantum impurity problem, a bit like resonant tunneling in a Luttinger liquid. So for that purpose, you basically look only at 2 linear combinations of these boson fields, namely the W minus, we just discussed, which is physically related to charge fluctuations on the central island. And since we want to probe the electric current, we need a second one, which is this field W plus, which is the sum of the field here and here, times 1/2. And the time derivative of this linear combination is related to the electric current through the interferometer. Yeah? And now you can integrate out all the boson fields, keeping these 2 linear combinations via Lagrange multipliers, and then also integrate out the Lagrange multipliers, because all these modes are Gaussian. They are quadratic. You can integrate them out, and thereby you have a quantum impurity problem, an action, effective action, just for these 2 fields. And what you need to compute to get the AC conductance in linear response from the Kubo formula is the equilibrium current-current correlation function, K of omega, for Matsubara frequencies omega, and then finally you will do an analytic continuation into the real plane with a positive imaginary part. So this is the equilibrium current correlator, and it involves this W plus field. So the Fourier component of it is given by this tilde W plus with our action. That's the task what one has to compute. And Here I will focus on the limit of small gamma. So this gamma term, due to the edge vortices, it is a relevant perturbation under the renormalization group, meaning it grows as you go to lower and lower temperature. So you cannot treat it by perturbation theory at very low temperatures. You have to stop at a temperature of order gamma. So if gamma is less than T or V over L, or the bigger of these two scales, you can treat it in perturbation theory. And so what we get in perturbation theory at low frequencies, low meaning gigahertz regime, is this result here. So the conductance at frequency omega is a DC conductance plus I omega. There's again this -1 to the NV factor, and then a difference of kinetic inductance of the Majoranas and an effective capacitance. And then there are terms of order omega square. We did the perturbation theory up to second order in gamma, but basically the second order just renormalizes the first, and it doesn't give you really new things. Now, the first thing I want to say is that the DC conductance here is simply the same as we had in the Foucault Nielsen-Akhmarov Benacker interferometer. So it's not affected at all by edge vortices or by tunneling. Why is that? It's a very simple reason. What comes in here must go out here. I mean, whether you re-scramble them doesn't really matter. So the conductance is in effect just E squared over H times plus or minus 1, depending on the number of vortices. So this braiding is sort of something that happens in time. And so you need to go to finite omega to really see traces of it. So this kinetic inductance of the Majoranas is basically just the length the Majorana travels times the density of states. So it's a constant. But the most interesting piece is now this effective capacitance, and this quantity contains the information about braiding, as we will see on the next slide. This quantity is measurable by measuring the phase delay between the current and the voltage. Yeah? And here is the result in this perturbative regime. So, of course, it's linear in gamma since we did perturbation theory. And there are two remarkable things. The most remarkable one is it has this cosine dependence on alpha, shifted by a term that has this S sigma on board, this topological spin. And alpha here is a tunable phase. It contains the Majorana fermion tunneling amplitudes, and it contains this offset charge that we can change by a backgate parameter. So in an experiment, you can tune this by changing gate voltages and then look at how this effective capacitance changes. That's shown here in the inset. As a function of alpha, the C effective should show oscillations, and the offset from 0 will tell you what is S sigma. And this topological spin is a direct signal for anyon braiding, as shown in this paper by Kitaev. So if you think in terms of up and down sigma, so this is the top and the bottom edge at a given space point. If you exchange them, you would pay this factor e to the 2 pi I S sigma. And now, in principle, in the calculation, we see this directly. You have interference of different processes. For instance, one process would be you don't exchange at -L, but you exchange at +L. So there's a process like this. Or you exchange at -L and don't exchange at L. There are also more processes, but the interference of these two really gives you this offset. So that's this interference, and that basically can be thought of as a braiding of these Majoranas around each other, of these Ising anyons around each other. So if you can see this oscillatory dependence and measure the offset, it is equivalent to showing anyon braiding. And in addition, if you look at temperatures that are large against V over L, You can convert the sinh into an exponential, and then you see on a log scale, these should be just straight lines, and the slope allows you to read off the conformal dimension. And what you should get is that H sigma is 1/16 and S sigma is also 1/16. Yeah. So if you see this in an experiment, I would say it's very strong evidence for a non-abelian braiding obtained by just measuring a conductance or an effective capacitance. Okay, that's it. So I've discussed topological quantum computation on a very basic level, edge vortices as flying Majorana zero modes, and then presented our proposal for how one could see Ising anyon or Ising anyon braiding by measuring the conductance or the effective capacitance. Thanks for your attention.
Thank you very much, Reinhold. Any questions?
And thanks, nice talk. You mentioned this perturbative result. So I was wondering if this mobile impurity problem also has a strong coupling limit. And
in the paper, we also address that. So if you go to the opposite limit, large gamma, which is less relevant experimentally, then you basically can perform an instanton analysis, because then if you look at this action here, if this gamma is very large, then you will basically pin the cosine to the minima of the cosine. And then the leading processes are tunneling between these minima, so-called instantons. And so we have done this calculation. One doesn't see clear evidence for braiding in this limit. So it's better to go to the small gamma limit in order to see braiding. And that's also the limit that in practice will be much easier to achieve in experiments. I mean, to get a huge a huge phase braid is difficult. Yeah. But the full crossover, I think then one has to do numerics, or maybe there's a CFT way of solving this. But
Can I ask another question? Also, I was wondering, usually when you started with braiding vortices in the bulk to implement the unitary transformations, would these flying anyons also be useful for that? Because now they're coupled to Kepler's edge modes, and
of course, I mean, to really do topological quantum computation in the end, one has to look at it. I mean, these flying anyon qubits could be useful to transfer information from one side to the other, for instance. But since they can braid around static vortices, it also offers you certain flexibilities. Yeah, but that's really something that would come later. I mean, then one has to look at more complicated devices with multiple edges and so on. Yeah.
Thanks for the nice talk. So you mentioned that this gamma, if I took it to the large limit, you don't see any evidence of braiding or something.
If gamma is very large and you go to this instanton limit, we can compute it, and sort of the signal gets blurred and more complicated, and it's not so easy to extract. You can find the details in the paper, but to really nicely see it from this cosine shifted by the topological spin, it's best to stay in the small gamma limit.
I see. So what the parameter? So is this gamma connected to any parameter in the book, or just?
Oh yeah, I showed it. Was here. So this is the phase slip rate. So basically, you can tune it by changing the EJ. So the Josephson energy of these line junctions, and the Josephson energy of the line junction is basically related to how thick the barriers are. So if you make these very thick barriers, then EJ is small. But we want to be in the limit that EJ is large against EC. So a large capacitance and a large Josephson energy, so rather thin transparent barriers. So this rate is to a large extent tunable. It's usually in a gigahertz regime, yeah. But there is a certain freedom over orders of magnitude where you can flexibly change it. I should say there are groups working on implementing this now. So in Cologne, there's the group of Yoichi Ando, for instance, that try to implement things like this.
I see. Thanks.
So I didn't understand. Is it a decoherence effect, or is that's a unitary operation?
That's a unitary operation, yeah.
Which allows you to effectively to pass anyons from one edge to the other.
Exactly, yeah.
And that's how you braid it.
Yeah.
And when they say that, well, let's say your conductance detect braiding, it means that you can measure it before and after this operation, and then you'll see. What exactly will you see in this case?
So the prediction was that what you should measure is you measured the conductance from here to here, but at finite frequency. So you apply AC voltage with frequency omega, and then you will also get a current I of omega. You divide both of them, get G of omega, and you look at the leading term in omega. The DC conductance will not tell you anything, but the AC conductance, so the leading term in omega, should have this structure. So from that, basically, you measure the phase delay between the current and the voltage, and thereby you can extract this effective capacitance. And when you analyze that as a function of this alpha parameter, this tunable phase, for instance, you change this backgate voltage defining the offset charge, you should be able to see this type of oscillation, and that is then the evidence for braiding.
So this conductance mean I see, for example, in the formula that you can measure statistics in this case, but when you say you can see the braiding, I'm not
the
sure.
The braiding is sort of hidden in the finite frequency response of the system, because that is it's basically this picture here, the braiding, meaning that one time you go like this, and there are other paths where you don't do this exchange here. So, but you have to sum over all of them because they are all possible, and there are interference terms that show up in the conductance. And these interference terms produce exactly this cosine term. So in that sense, it's braiding because the particles move like this or like this. And all these processes need to be taken into account, and then you will end up with this.
Confusion is whether you see, I mean, can you perform a braiding and then somehow see this in the...
Of course, no. In a conductance measurement, you basically have an average over many of these. It's not an individual braiding event because conductance is usually measured by a long time interval, and then basically you average over many braiding events. But the braiding shows up through this even on average, because there's interference between different processes, between different trajectories.
Okay, thank you. More questions? Okay, if not, let's thank Reinhold again.
Thank you.